Hello, we're looking at hydrides and organometallics reacting with acid derivatives. We've been doing a variety of nucleophiles reacting with acid derivatives, so now we'll look at these partially ionic. So this mechanism, if we look at it, remember the hydride, we can simplify this mechanism. It's a little oversimplified, but consider this to be an H- reacting with our carbonyl. Break the pi bond, and we form the tetrahedral intermediate. And because there's a leaving group, we can pi donate back down and kick off the chlorine. That gives us the aldehyde intermediate, which is still an electrophile. And we've seen hydrides reacting with aldehydes before, so we can easily imagine that excess hydride in solution will react with that aldehyde, forming the alkoxide, and then under acidic conditions, this will be protonated, forming the alcohol product. Similarly, we can see the organometallic reagents such as the Grignard. The carbon with the lone pair on it will attack, break the pi bond. We have a chlorine leaving group, so we'll do a pi donation to form the ketone. Ketones are still relatively reactive, and so the methyl will react again, forming our tertiary alcohol in this case. However, we're going to introduce some new, these aren't Grignards, these are called cuprates or Gilman reagents. This is a carbon with a lone pair again, but there's two of them, there should be a 2 there, bonded to the cuprate. And in this case, again, this is reactive and it will react with the very electrophilic acid chloride. You'll do your pi donation and get the ketone. But in this case, the cuprate is too weak to continue this reaction. Cuprates are much weaker nucleophiles than the Grignards. And so this stops at the ketone. So if we look at our hill of reactivity, we see our acid chloride and our anhydrides, and they'll react with the cuprates. They'll react with sodium borohydride, Grignards, or lithium aluminum hydride, and will form either the ketone or the aldehyde, depending on what my nucleophile was. If it was an alkyl group with the cuprate or the Grignard, we'll form a ketone. If it's hydride, we'll form the aldehyde. At this point, if we started with the acid chloride, the sodium borohydride could continue to react, but we see the cuprate is too weak to react with the ketone or aldehyde. But then this is also an indicator of whether it will start with the other lower on the hill. So sodium borohydride will react 2 times with an acid chloride or an acid anhydride, react to form the aldehyde, and then react to form the alcohol. But it won't even start reacting with the ester or the thioester. A Grignard will react with the ester, thioester, ketone, acid chloride. If it starts with any of the acid derivatives, you'll form the ketone intermediate, and it will react a second time to give you that tertiary alcohol. Grignards, though, won't react with the amides, the carboxylates, or the carboxylic acids. The only thing that will react with everything 2 times is lithium aluminum hydride, well, of these 4 reagents. So you need to understand the nucleophilicity of these reagents as well as the electrophilicity of your starting carbonyls. So in summary, we'll see Grignards react 2 times to give you an alcohol product, whereas the cuprates will usually only give you the ketone, and they will only react with the starting acid chloride. The Grignard will react with, this could be an acid chloride or the starting ester. And we'll see that lithium aluminum hydride will react with any of the acid derivatives to give you an alcohol. whereas sodium borohydride will really only react with the acid chloride or with ketones or aldehydes and won't give you a product. This is essentially no product if you start with the amide or the ester or the carboxylic acid. So it's worth making sure you do some practice recognizing which of these things will react and which won't, looking at the variable reactivity of both the nucleophile and the electrophile.